All right, lesson 1.7 talks about combinations of functions. Two functions can be combined to create new functions. So it says let f and g be two functions with overlapping domains. Then the algebraic combinations of f and g are defined for all x common to both domains. So we have the sum. If you see f plus g with respect to x, that's the same thing as taking f of x and adding g of x to it. The difference, f minus g with respect to x, is equal to f of x minus g of x. And then the product, f times g with respect to x, means we're going to take f of x and multiply it by g of x. And then the quotient, f divided by g with respect to x, means we're going to take f of x divided by g of x. And also remember, though, g of x cannot equal 0 because we can't have 0 in the bottom of the fraction. All right, so real quick, though, before we move on, let's look at this. You see how this says f plus g and then it has an x? That doesn't mean times x. That's with respect to x, meaning that x is going to be our variable. This is notation. Notation, no touch, okay? So don't try to solve for x. Don't do anything with it other than to know that it means we're going to take our f of x and we're going to add g of x to it. All right, so then it tells us note on the domain. In each case, the domain of the new function consists of all numbers that belong to both the domain of f and the domain of g. The zeros of the denominator are excluded from the domain of the quotient. So let's do this. So example 1, it says let f of x equal 5x minus 8 and g of x equals 7 minus 2x squared. And we're going to find f minus g with respect to x. So remember that f minus g with respect to x just means we're going to take f of x and we're going to subtract g of x. So let's first just set that up. So we're going to take f of x, which is 5x minus 8, and we're going to subtract g of x, which is 7 minus 2x squared. Do I need to put them in parentheses? Yes, you do, because we're not just subtracting the 7. We're subtracting the 7, and we're subtracting the negative 2x squared. All right, so then remember, to get rid of the parentheses, you need to distribute whatever's in front of them. Well, this first one doesn't have anything, so we're going to put a 1 there. So it's going to give us 5x minus 8. And then the second one has a minus, so we're going to put it as a negative 1 and distribute it. So minus 7 plus 2x squared. Once we get rid of the parentheses, then all we have left to do is combine like terms, and we want to write our exponents in descending order. So start with the largest one. So we have an x squared, so we have just a 2x squared. And then our x, which is just a 5x. And then notice we do have like terms here. So negative 8 minus 7 is negative 15. And so there is our solution. Now B says we want to evaluate f minus g of 4. So we have two choices here. This means that we can take f of 4 minus g of 4, or wait, we already did f minus g with respect to x, and we found what that equation was. The only difference between that, f minus g with respect to x, and what we're looking for right now is the fact that x is being replaced with a 4. So we can actually take that equation that we just found and we can replace x with the 4. So we're going to do, it was 2x squared plus, oops, I forgot my x when I wrote that. Hopefully you caught that. So plus 5x minus 15, and then we're going to replace our x with a 4. So we get 2 times 4 squared plus 5 times 4 minus 15, and let's just work that out. So 4 squared is 16, 5 times 4 is 20. That's what, 32 plus 20 minus 15, and that's what, 37 is our solution. All right, we're doing the same thing on example 2, but now we've got to also give the domain. So look at the first thing. It tells us f of x is equal to x cubed and g of x is equal to square root of x plus 1. Find the following and give the domain of each. So f plus g. So we're going to take our f function and we're going to add our g function. So we're going to take x cubed and we're going to add the square root of x plus 1. Well, remember, let's get rid of the parentheses. So we have x cubed plus the square root of x plus 1. The only way we can add or subtract with radicals is if they have like radicals. And that x cubed doesn't have a radical at all. Therefore, this is simplified. Now, when we go to find the domain, remember we had talked about restrictions on the domain. We had said domain is negative infinity to infinity unless we had a fraction in which the denominator cannot equal 0, or we had an even root radical in which we had to set the radical greater than or equal to 0. Here we have that even root radical. So we're going to set that square root of x plus 1 greater than or equal to 0. Oops, wrong space. Sorry about that. So the square root of the x plus 1 is greater than or equal to 0. Well, let's get rid of the radical. So really, we got x plus 1 is greater than or equal to 0. Move the 1 over, and we find that x is greater than or equal to negative 1. Remember, we talked about if we need a number line to help us to write this in interval notation, we can use it. So here's my negative 1. It's equal to, so it's got a closed circle. I'm looking for numbers that are greater than. Greater than numbers are to the right of negative 1. And so I can see my interval right there, so I know it's negative 1 to infinity. Infinities always have parentheses, and we said it was equal to at the negative 1, so we're going to put a bracket. B, or not B, but the next one is f minus g. So we're going to take f, x cubed, minus g, which is the square root of x plus 1. So let's get rid of the parentheses. So we get x cubed minus the square root of x plus 1. Again, I only add and subtract with radicals if they're like radicals. X cubed doesn't have a radical, so that's simplified. Now notice that it has the same restriction that the previous one did, right? It has that square root of x plus 1, and we know that's got to be greater than or equal to 0. And so I already worked it above, so I'm not going to rework it again. We're just going to get the same answer from negative 1 to positive infinity. All right, C, or the next one says f times g. So we're going to take f, and we're going to multiply it times g. Well, remember when you're multiplying with radicals, you only multiply what's on the outside together and what's on the inside together. So here I just have an x cubed on the outside, and I have a x plus 1 on the inside. So we're just going to have to leave it as x cubed times the square root of x plus 1. Again, when we go to do our domain, our restriction is we've got that radical, so we just know that it has to be greater than or equal to 0. And so therefore, we're still going to get negative 1 to infinity. And then last, we've got this f divided by g. So we're going to take f of x, and we're going to divide it by g of x. Now the only thing we can do there, we can't factor the top, we can't factor the bottom. So the only thing we could do is try to rationalize that denominator, but we're not going to worry about that at this point. All right, so this is simplified. Now my domain, I've got the two restrictions. I've got the fact that we still have that radical, so it's got to be greater than or equal to 0, but I also have the fact that we have a fraction, and so remember the fraction says that the denominator cannot equal 0. Well, this says it equals 0, this one says it can't. So therefore, when we put them together, we have to take out the equal to. So we end up with the square root of x plus 1 is only greater than 0. So when we solve this, we get the same number, but this time it's not equal to. So we know it's going to start at negative 1, not equal to, so use a parenthesis, and go to infinity. All right, composition of functions. When you compose a function, you're plugging one function into another function to create a new one. And so it is, notice the notation here. It says the composition of the function f with the function g is defined as f composed of g with respect to x, or it can be written as f of g of x. The domain is a set of all x of g such that g of x is the domain of f. So you need to look at where your the domain of your input and the domain of your output. What makes them both true? Where do they overlap to get your domain of your composition? All right, so example 3 says let f of x equal x squared plus 2x minus 1, g of x is equal to 1 over x minus 2, and h of x is equal to the square root of 3x. Find a rule for each of the following and state the domain of each. So the first one here is f composed of g with respect to x. So when we write this out, I like to write it as f of g of x. Because remember, if I wrote f of 4, I would take 4 and plug it into my f function. This says I'm going to take g and plug it into my f function. So I'm going to let f be what I call my skeleton, which means I'm going to write out the f equation, but I'm not going to put x. I'm going to put parentheses where there's an x. So f is on the outside, so it's my skeleton, which is x squared plus 2x minus 1. And we're going to plug g of x into those parentheses now. So when I plug in the g of x is 1 over x minus 2. And so let's simplify this a little bit. Remember that 1 over x minus 2 squared, anything squared means times itself. And then plus, remember when you're multiplying with fractions, you're going to multiply straight across. So I'm going to change that 2 into a fraction. So it's 2 over 1 times 1 over x minus 2. And then we just got this minus 1 at the end. So when I multiply this out, multiplying straight across, I get 1 over, well, notice this is just x minus 2 times itself. And since I have an x minus 2 later in the problem here, I'm going to leave it like that. You can work it if you want to, but you don't have to. And then here we're going to multiply straight across. So we get 2 over x minus 2. And then minus 1. And unless we want to find a least common denominator so that we can combine all of these, I will let you stop here for this. Reason is because this is enough that I can go ahead and find my domain. So remember, your domain, you have to look at your input and your output. So I'm going to change colors here. So for domain, first, let's look at our input. The input was 1 over x minus 2. It was our g of x. So we know if we have 1 over x minus 2, then that means that it's a fraction and our denominator cannot equal 0. So I'm going to add the 2, and so I get x cannot equal 2. Now when I look at my output, that's what's above. I'm not going to rewrite all that. So for my output, what's my restriction? Again, it's a fraction, right? And the fraction says the denominator cannot equal 0. So I see my denominator is x minus 2. Even though that other one is x minus 2 squared, it's still the same. It's going to have that x minus 2 cannot equal 0. We solve this one, add the 2, and we find x can't equal 2 as well. If you need to, use a number line to help you. So we have negative infinity to infinity. We've got that 2. And we said x cannot equal 2, which means everything below 2 is included. Everything above the 2 is included, just not the 2. And so we can see we're going to have 2 pieces to our domain. So our domain is going to be that negative infinity to 2 not included, union 2 not included to positive infinity. And so there is our domain. B, g composed of f of x. So this is the same as g of f of x. So now g is on the outside, so g is my skeleton, and we're going to plug f into it. So g was 1 over x, might need a little bigger one than that, minus 2. And we're going to plug f of x into that. So f of x was x squared plus 2x minus 1. Well, in that denominator, I see that we can get rid of the parentheses. So this is 1 over x squared plus 2x minus 1, and then we have that minus 2. And we do have like terms, so we can combine it. So we get 1 over x squared plus 2x minus 3. And so we're simplified here. And now we need to work on our domain. So our domain, remember we got to look at our input. The input was f of x. Well, the input was just a polynomial. It had no fraction and it had no even root radical. Therefore, the domain of my input is negative infinity to infinity. My output had a fraction, and so that meant that that denominator cannot equal 0. So x squared plus 2x minus 3 cannot equal 0. And so we need to factor this. It's a simple trinomial. It's x and x, what multiplies a 3 that subtracts the 2, 3 and 1. 2's got to be positive, so the 3 is positive, and then it makes the 1 negative. And remember, this cannot equal 0. So that means that x plus 3 cannot equal 0, and x minus 1 cannot equal 0. So subtract the 3, so x cannot equal negative 3, add the 1, x cannot equal positive 1. So I know that my input says they all work for it, but my output says no, not the negative 3 or the 1. So when we put that together, we can see that negative 3 is going to be an open circle, 1 is going to have to be an open circle, and then they said everything else here works. So therefore, oops, I forgot my infinities. There they are. And so we can see that we have 3 intervals there. So our domain is going to be negative infinity to negative 3, union, negative 3 to 1, union 1 to infinity. And so there's the domain of our composition. Remember, the domain of the input and the output only help us find it. And then C. C says F composed of H of X. So I'm going to move this up so we can see it better. Give myself a little more room. All right, F composed of H of X. So we know that that means, oops, sorry, turn my pen off. Let me get it back on. So that means we have F of H of X. So F is on the outside, so it's my skeleton, and we're plugging in H of X. So F is my skeleton, so x squared plus 2x minus 1. And we're plugging in H of X, which is the square root of 3x. And so we're going to simplify if possible. Well, the square root of 3x squared, the square and the square root cancel, so we get 3x. 2 times the square root of 3x, but we can't do anything with it, so it's just 2 square root of 3x, and then minus 1. I don't have any like terms, so there we are simplified. So now for the domain, remember we have to look at the domain of the input. My input was H of X. It was a square root of 3x, which we know the square root of 3x has to be greater than or equal to 0. So square it. So 3x is greater than or equal to 0. Divide by the 3. So we just get x has to be greater than or equal to 0. Then you got to look at your output. Well, my output, no fraction, but I do still have that square root of 3x. So the same thing, right? So I don't really need to work it twice. I can already see it's going to be x is greater than or equal to 0. So they're the same. So if I look at my number line, if x is greater than or equal to 0, it's going to start at 0, and greater than is to the right. So I can see it's between 0 and positive infinity, and 0 is included, so it gets a bracket. And so there's our domain of this composition. And then D, H composed of f of x. So H of f of x means H is my skeleton and f is what we're plugging in. So H is my skeleton, so the square root of 3x, and we're plugging in f of x, which is x squared plus 2x minus 1. So underneath the radical there, we can distribute the 3. So we would get square root of 3 times, 3 times x squared, and 3 times 2x, and 3 times negative 1. No like terms, can't do anything else, so this is what we get. Now for the domain on this one is tricky, and it's something we hadn't talked about. So the 3x squared plus 6x minus 3 doesn't factor. So if you end up with one that doesn't factor, for right now, you don't have to worry about the domain. So don't worry about it because it comes out that it's irrational. It actually, but we haven't talked about together how to find it yet, so I don't expect you to do it. All right, so let's keep going then. So now let's do the opposite. Now we're going to decompose the functions. Remember, decomposing means something's coming apart, okay? So when you decompose a composite function, you're finding the components of the composition. Look for the inner function and look for the outer function. So we're going to take this apart. Now I know, like, this is my f of g of x, and we're looking for what is f of x and what is g of x. So example 4 says, for each function h, find functions f and g such that h of x is equal to f of g of x. So notice our inside there is g of x, and that leaves our outside to be the f of x. Now these are really super easy. Don't overthink them, okay? Now your inside can never be just x. Okay, it has to be x plus something, x minus something, x raised to an exponent. It can't just be x itself. So inside, you want to look for what is inside of something with the x, whether it's inside parentheses, inside a radical, inside absolute value bars, inside the denominator of the fraction, inside the numerator of the fraction. It's inside somewhere with that x, okay? And so when we look at this first one here at A, notice we have an x plus 3 inside the parentheses. So let's let our inside be x plus 3. Then what I want you to do is where that x plus 3 is, I want you to put a big X over it. F of x is what you have left. F of x now is, what does this actually have? I have an x and it's raised to the second power. So my outside is going to be x squared. So let's try B. B says h of x is equal to 1 over x minus 5. Our inside, what is with the x? Well, in the denominator, we have x minus 5. So let's let that be our inside, and let's go x that out. And so what do we have left for the outside? Well, we have 1 over our x. C, h of x equals square root of x plus 2. On the inside with x, we have an x plus 2 under the radical there. So write it down for your inside and then x it out. And what's left? The square root of that x. And then the last one, notice there's more than one x. So whatever we let be our inside has to be the same for each of them. And so we notice, though, the x is inside parentheses both times with a minus 2. So let's let our inside be x minus 2. And then, because there's more than one of them, we're going to replace them both with an x. And then read what's left for the outside. We have x squared minus 4x plus 5. And that, guys, is decomposing functions. Don't try to make it hard. But the question is, though, is that the only answer we could get? On these, yes, it was. But look at example 5 here. Example 5 says, let h of x equal the square root of 3x squared plus 1. Write h as a composition of functions in 2 different ways. So sometimes there's more than one answer. That one, each of them was just x. So there was only one answer. So let's look at example 5. Let's find f of x and g of x. Remember g of x, because we're just using the fact that this is, I'm going to say h of x is equal to f of g of x. If they don't specify, just you're allowed to assume that that's what they mean. All right, so g of x is our inside function. So if we look, there's a 3x squared plus 1 inside with the x. And so remember, after you write it down for your inside, x it out, and f of x, the outside, is what's left. We have the square root of x. Oops, I forgot my square right there. All right, but is that the only answer? No, it's not. What if I said, well, I think I want my inside here to just be the 3x squared. So we could do that. So we're going to put 3x squared. Remember, x it out. And then the outside is what is left. Well, now we have the square root of that x, and we still have that plus 1. But I even see another one there. So what if, and I remember, our inside can't just be x, but our inside can be that x squared, okay? So we're going to take that x squared and x it out, and that lets our outside then be the square root of 3x plus 1. So all 3 of those answers will work. Now let me show you one that won't work, because we're able to separate them some, but you got to remember PEMDAS, okay? You multiply before you add. So we cannot, whoops, what did I just do? I don't know. All right, so we cannot say, I want to make this inside be an x squared plus 1, because that x squared is being multiplied with that 3 first before we're allowed to add the 1. If I want my inside to be x squared plus 1, it had to already be in parentheses together, okay? So you can't separate something and make it where PEMDAS won't work. Because the x squared is being multiplied times a 3, you can't just put the x squared with the 1 unless it's already separated. So just watch out for that. All right, so I think I'm going to stop here for video 1, and then we'll pick up on video 2 in just a moment.